Yes. Hello, friends. Welcome to the session. Still now, in the DC to DC converters, I discussed about in detail about what exactly buck regulator or step down chopper in both continuous and discontinuous mode. That concept I discussed. The next converter in DC to DC converters based on output voltage level, that is boost regulator or step up chopper. Now we'll see what exactly circuit of boost regulator or step up chopper and what is the analysis. Okay, we'll start with the step up chopper or boost regulator. Step up chopper. This is step up chopper, or it's also called boost regulator. Boost regulator. Tell me, can you draw the what is the circuit of step up chopper or boost regulator? I told already how to identify boost regulator or step up chopper. Inductor is at source side, and this is the switch. Switch or chopper. Parallelly draw the circuit, don't wait. Diode, capacitor, with load. Okay, this is capacitor. First, I will discuss the concept with respect to continuous mode. At the end, I will discuss with respect to discontinuous. This positive, negative, V. So this is inductor current IL. This is L. The supply is VDC. This is positive, negative. This is switch or chopper. This is I. Voltage across inductor is VI. This is boost regulator or step up chopper circuit. You know this one operation is nothing but a one on and one off. Chopper is on. If chopper is on, diode is under off state. But in this circuit, whatever the diode is there, it is not a freewheeling diode, it is a feedback diode. Because it supplies the current to the load through source. That you will see in the next case. That's why it is not a freewheeling diode. That's why it simply I taken diode. It's a feedback. Chopper is on, diode is off. What is the equivalent circuit? Then inductor storing the energy. Inductor storing the energy. Inductor storing the energy. Okay. Now, inductor storing the energy means for the circuit, equivalent circuit. Plus minus VL. Chopper is on. Chopper or switch is on. This is VDC. Plus minus. Diode is off state. Capacitor. This is load. Okay. This one is IC. This one is I naught. Positive, negative, V naught. Diode is off state. Which is on. From this, what is the observation? You tell me. What is KVL for this? VL equal to VDC. VL is nothing but a L into di by dt. That is DIL by dt. This is IL current. Then what is this? Is KVL. And this is KCL. Apply KCL here at this node. IC plus I naught equal to 0. What is IC equal to? Minus I. IC is nothing but a C into dVc by dt. This is according to KCL. Same analysis what you done in the step down chopper, same procedure you follow. Okay. This is voltage equation, this is current equation. Voltage equation written according to KVL. Current equation is written according to KCL. Next. But one operation is nothing but one on and one off. Chopper on, chopper off. If the chopper is off, diode is on. Then what is the equivalent? Chopper is off, diode is on. It's plus minus VDC. Plus minus VD. Chopper is off. Diode is on. Yes. Sorry. This diode is on state. It's capacitor. This is IC. This load is I naught. This is load. Okay. Load current is I naught. Voltage across the load is V naught. Then what is current? IL. This is inductor. Voltage across the inductor is VL. This equivalent circuit, if the chopper is on, diode is, chopper is off, diode is on. Then according to KVL, you tell me. According to KVL, VL plus V naught equal to VDC. What is VL equal to? VDC minus V naught. According to KCL, you tell me. IL equal to IC plus I naught. What is IC equal to? IL minus I naught. This is KCL. Where VL equal to L into di by dt during off state. Where IC equal to C into dV by dt. IC written as C into dV by dt. See, don't confuse with this. You write VL equal to L into di by dt. You write V naught equal to I naught into R. if it is a resistive load. IC equal to C into dV by dt. What is IL equal to L into di by dt? What is I naught equal to V naught by R? Like that also you express. In terms of differential equations also you can express, no problem. Okay. Then this is VL equal to VDC minus V naught, IC equal to IL minus I naught. Here also same. To write IC equal to C into dV by dt, I naught equal to V naught by R, VL equal to L into di by dt. Like that also you can express. Okay. In different books they are following different ways, but directly instead of differential, directly I written this equation. This is freewheeling diode is, sorry, not freewheeling diode, it's a diode. Diode is on, chopper is off, diode is on. Here chopper is on, diode is off state. Now, to analyze this one. Now, waveforms is same. This is a switching, T on, T off, again this is T on. Okay, this is a switching time. Switching time. We can take T on, T off, this is T on. This is switching time. On state inductor storing the energy, off state inductor releasing the energy, again on state inductor, again off state inductor releasing the energy, same way. Then this is the source current or switch current waveform. Mainly this is source current or switch current waveform, and this is a diode current waveform. Here it is not a freewheeling diode, it is a diode current waveform. Waveforms are same what I discussed in this buck regulator, same waveform time. But here the capacitor current waveform will be changes, that you concentrate. This waveform will be changes here. Remaining waveforms are same, only this waveform will change. Now how we are getting this waveform, that you concentrate. Listen please. If the chopper is on state, this circuit completely disconnected, you have this circuit only. That means if chopper is on state, switch is on state, who supplies the current to the load? Capacitor supplying the current to the load. During switch is on state, capacitor is supplying the current to the load. That's why this, assuming that we are supplying the constant current to the load, this operation is applicable for constant current. We are supplying the constant current to the load means IC equal to minus I naught. In this case, IC equal to minus I naught. That's why it is a constant current. IC equal to minus I naught. IC equal to minus I naught. Constant minus I naught. IC equal to minus I naught. Now, if the switch is on state, now capacitor is charging. But what is IC? Is not IC equal to I naught. IC equal to IL minus I naught. IL minus I. Slightly we can get the curve like this. It is not I naught. This is IL minus I naught. Again we can get minus I. This is IL minus I naught. Like this we can get the wave shape. This is for which one? Capacitor current wave. Only capacitor current waveform is changes from buck regulator to voltage across the capacitor waveform is also changes. But I am not drawing, only capacitor current waveform I am drawing. This is IL minus I naught. If the switch is off state, IL minus. This is minus I naught. Actually, this is minus I naught to plus I naught, but slowly current will be decreased. Clear? Okay. Yeah, this is the capacitor current waveform. Okay. Now, with this knowledge, now if you want to do the analysis means first you start with voltage second balance. Okay, you go with the first one is volt second balance. Volt second balance. Then what is volt second balance? VL on into T on plus VL off into T off. is equal to 0. What is VL on? VL on is VDC. VDC into T on plus. What is VL off? VL off is VDC minus V naught into T off is equal to 0. VDC into T on, that is VDC minus V naught into T off. Shall you write like this? VDC into T on equal to, bring this side, V naught minus VDC into T off. Correct? Yes. What is T on? T on equal to dt. What is T off? T off is 1 minus d into t. 1 minus d into t is equal to V naught by V naught minus VDC by VDC. Correct? Yes. Shall you write like this? D by 1 minus d equal to V naught by VDC minus 1. What is V naught by VDC equal to? D by 1 minus d plus 1. Then what you get? V naught by VDC equal to 1 by 1 minus d. Then what is V naught equal to? VDC by 1 minus d. This is average output voltage formula in the case of which one? Boost regulator. In boost regulator, what is the average output voltage? V naught equal to VDC by 1 minus d. Okay, this is first parameter calculated in boost regulator or step-up choker. Now down, quick. In the case of step-up choker or boost regulator, therefore average output voltage equal to average output voltage or average load voltage. V naught equal to VDC by 1 minus d. In general, for 0 less than d less than 1, V naught greater than VDC. Hence, it is a which choker? Step-up choker. Hence, it is a step-up choker. A step-up choker. Then what is the average load current? You can write I naught equal to V naught by R. This I naught equal to V naught minus E by R. This is for R comma RL load. This is for RE comma RLE load. Okay. Now second parameter. For that you do the current, that is current second balance, ampere second balance. Ampere second balance. Then according to ampere second balance means IC on into T on plus IC off into T off is equal to 0. In on time, what is capacitor current IC equal to minus I naught into T on. This is minus I naught into T on. Correct? IC equal to, in on time, what is IC calculated? Minus I naught. What is IC off time? IL minus I naught into T off is equal to 0. Then shall you write like this? I naught into T on is equal to IL minus I naught into T off. What is T on? dt. What is T of IL minus I naught into 1 minus d into t? Tt cancel. Shall you write like this? S. Then di naught equal to 1 minus d into IL minus I naught. Now from this, we simplify this. D by 1 minus d equal to IL by I naught minus 1. Shall you write like this? D by 1 minus D plus 1 equal to IL by I naught. Now from this, what we can write? D by 1 minus D plus 1. Shall we simplify this one? 1 by 1 minus D equal to IL. Then what is IL equal to 1 minus D into I naught. This is IL average. That's why in the case of boost regulator, IL average is not equal to I naught. This is important. Here it is not equal to I naught. In the case of boost regulator, IL average is IL. That equal to 1 minus D times of I naught is not equal to I naught. This is the second parameter. Do this quick. This what is IL here? Not I naught by 1 minus. If IL you want, na? I naught by 1 minus. This is IL average. IL average is not equal to I naught. This is the second parameter. This is the first one and this is second. Yes. Okay, clear? Go for third one. Third one is for lossless chopper. For lossless chopper. Or the condition. Same procedure what I explained in the buck regulator. For lossless chopper, what is the condition? Input power equal to output power. What is the input power? Vs into Is. What is the output power? V naught into I naught. Then what is V naught? You write, you tell me. V naught equal to VDC by 1 minus D into I naught. Okay. Then VDC by 1 minus D into I naught. This is VSC is nothing but a VDC. VDC into IS. Okay. Then VDC into IS means VDC cancel. What is IS equal to I naught by 1 minus D. You take notation is either VDC or VS notation. Here I taken VDC notation. Input power equal to output power. That is instead of VS, instead of VDC you also take VS also, no problem. Then in the circuit I represented VDC now, that's why I taken. Then IS equal to I naught by 1 minus D. This is average source current. Average source current. Fourth one. Calculation of peak to peak inductor ripple current. Inductor ripple current. Calculation of peak to peak inductor ripple current. To calculate peak to peak inductor ripple current, you take either on state or off state. You take during on state. Which is on state. What is VL equal to? L into DIL by dt is equal to VDC. Shall you write like this? During on state, current is changing from minima to maxima. Minima to maxima means peak to peak ripple current. That is L into delta L by T on is equal to VDC. Then L into delta L by T on is dt into VDC. Now from this What is the delta L equal to? Delta L equal to dVdC by FL. This peak to peak inductor ripple current. The peak to peak inductor ripple current. What is the delta L calculation? Then it is maximum. Again, no need to differentiate directly from this. What is the maximum value of duty cycle? 1. Okay. It is D is maximum. It is maximum. What is the maximum value of duty cycle? 1. That's why delta IL is maximum. It is maximum at D equal to 1. But in the case of buck regulator, where the delta L is maximum at the duty cycle equal to 0.5. But in the case of boost regulator, where the delta L is maximum at the duty cycle equal to 1. Then what is the delta L max? Delta L max equal to D equal to 1, you substitute VDC by FL. VDC by FL. This is over. Okay, this is fourth parameter. Then what is the fifth one? Once you know the delta IL, how to calculate IL minima? IL minima equal to IL plus minima na? IL minus delta IL by 2. But IL is not I not here. Okay. What is IL? This is IL maxima. IL maximum is this one. What is IL minima? IL minima equal to, this is minimum value on this minus this. This IL minus delta IL by 2. But here IL average is not equal to I naught. IL average is not equal to I naught. This is fifth one. What is the sixth one? What is the peak value? What is the average value of switch current? ISW average. ISW average. Same switch is average value of switch current during on state. During on state on same calculation we can get DIL. Average value of switch current equal to DIL. Average value of switch means like this. Switch is conducting during on state. It's supplying which current? Inductor current. Then in off state, this is T on. In off state, switch current is 0. DIL average. What is IL average? IL. DIL. What is the RMS value of switch current? RMS switch current equal to root DIL. What is the peak value of switch current? The peak value of switch current equal to IL max. What is the peak voltage across the switch? You tell me. During which condition voltage will appear across the switch? Off state. You know this circuit now. During off state, what is the circuit? You tell me. Switch is off state. Switch is off state. Switch is off state. This is the circuit. Then switch is off state. What is the peak voltage across the switch? This voltage plus this voltage. Then what do you get? VDC plus VL. VDC plus VL. That equal to which one? V naught. If the peak voltage across the switch equal to VDC plus VL. Because after reversing the polarity, inductor release the energy. This is minus plus VL. This is minus plus VDC. VDC plus VL. This is the peak voltage across the switch. When the voltage will appear across the switch means during on state. But in the case of buck regulator, what the peak voltage across the switch, we are getting only VDC. But here VDC plus VL. This is the sixth parameter. Understood? Hold on. Quick. Next. See the seventh parameter. What is the seventh one? Yes. This is fifth, sixth, seventh one is you calculate what the average diode current. You tell me average value of diode current, ID average, during which time diode is conducting on state. Diode is also carries which current? Diode, average diode current. Okay, diode is nothing, inductor current. IL into during which time it is conducting off state. T off by T. T off by T. Then what you get? IL into 1 minus T. What is ID RMS equal to? That is root of 1 minus D into IL. Because it's a constant current. This is IL average. This is IL average. Is nothing but IL. Root of 1 minus D into IL. IL average is nothing but IL. Next, eighth one. Calculation of peak to peak capacitor ripple voltage. Calculation of, this is IL average. This also IL average. IL average is nothing but IL. Okay. IL into square root of 1 minus 2. Don't confuse. Calculation of capacitor peak to peak ripple voltage. Peak to peak ripple voltage. Ripple voltage. That is delta VC. Then same, you know that Q equal to C into VC. Then delta Q equal to C into delta VC. Then what is the delta VC equal to? Delta Q by C. What is delta Q is? Delta Q is area under the current curve. What is the area under the current curve? The area under the current curve is constant because it's applying the constant current. Okay. Area under the current curve is, this is delta VC equal to delta Q by C. What is delta Q here? Area under the current curve. Shall we write like this? Yes. You write delta Q. You just like Q equal to IT. No? Q equal to IT. But instead of I, you take I naught. During which time? On time. It's applying the during on time. Then how to write T on equal to I naught into dt. dt. D into T naught. Okay. Then shall you write like this? Okay. dt. Q IT means I naught into T during T time. During T time. Or area under the current curve. Area under the current curve is nothing but a constant. Then shall you write like this? I naught, or otherwise this is during T on time. T on. T on is written as dt. This is correct. Q equal to 8. Why I am taking this formula? Because a constant current. Area under the curve. I naught into T on. If you want, this is a rectangular. Na? Rectangular area means length into width. Length is how much? Width. This width is I naught. Length is how much? During which time? T on. I naught into T on. That is I naught into dt. Area under the current curve only I am calculating. That is how you can write d I naught into T by C. Then what is delta VC, peak to peak ripple voltage? d I naught by FC. This is a peak to peak capacitor ripple voltage. Now tell me, this delta VC is maximum at D equal to 1. Because maximum value of duty cycle is 1. No need to differentiate again. When this value becomes maximum at D equal to 1. Then what is the delta VC max? What is the delta VC max? D by, that is D equal to 1, I naught by FC. Delta VC max equal to I naught by FC. It is maximum at D equal to 1. Clear? So this is 8th one. What about 9th parameter? Quick, do this. How to calculate 9th parameter? Critical inductance. Calculation of LC. What is the critical inductance? This you already know. Calculation of LC. Calculation of LC. What is the critical inductance? How to calculate critical inductance? To calculate critical inductance, what is the condition? IL minima equal to 0. The reason I told already. What is IL minima? IL minus delta IL by 2 equal to 0. Then IL equal to delta IL by 2. Delta IL by 2. What is delta IL? You tell me. Delta IL equal to dVdC by FL. dVdC by FL. dVdC by FL. Okay. Then what is IL equal to? I naught by 1 minus D. I naught by 1 minus D. D into VDC by FL. If IL is not I naught here. I naught by 1 minus D. What is I naught? You can write I naught is written as VDC by R. VDC by R into 1 minus D. That is dVdC by FL. VDC cancel. Then from this, what is the critical inductance? LC equal to R into critical inductance LC equal delta IL by 2. Delta IL by 2 means this is 2FL. This is 2FL. LC equal to R into 1 minus D. This is R into D into 1 minus D. D is not delta IL by 2. Yes, this calculated on dVdC. That's R into D into 1 minus D by 2M. This is critical inductance. This is corresponding to critical inductance. This resistance is critical resistance. Or D in R into D into 1 minus A, critical resistance. Critical resistance. Clear? Simplify this. Quick note down. See, you can write I naught by 1 minus D equal dVdC by 2FL, but you take I naught is you written as V naught by R. Previously I given wrong that, not VDC by R, it is a V naught by R. You correct that one. V naught by R into 1 minus D, that is dVdC by 2FL. Okay, then what is V naught? You write VDC by 1 minus D. In a boost regulator, what is V naught equal to VDC by 1 minus D. VDC by 1 minus D means 1 minus D into 1 minus D, 1 minus D whole square you can get. Then VDC by R into 1 minus D whole square, that is dVDC by 2F. Then VDC cancel. Now from this you simplify this, what you can get LC equal D into 1 minus D whole square into R by 2F. This is the formula for critical inductance. Clear? Understand? Please you correct that. In the previous slide I told that VDC by R, because I naught na, it is V naught by R. V naught by R. That you write. V naught I written. What is this V naught? VDC by 1 minus D. Okay. VDC by 1 minus D means already 1 minus D is there. That's why I get 1 minus D whole square. Okay. Then from this I calculated L. VDC cancel. L is nothing but a critical inductance. Corresponding to this critical inductance, this resistance is nothing but a critical resistance. Critical resistance. Okay. Then last one, 10th parameter is calculation of critical capacitance. 10th parameter is calculation of critical capacitance. What is the critical capacitance that you know? Critical capacitance CC. Calculation of critical capacitance. What is the condition to calculate the critical capacitance? The condition to calculate the critical capacitance is delta VC minima equal to 0. Then what is delta VC minima equal to 0? Then that is VC minima equal to 0. What is VC minima? What is VC minima? V naught minus delta VC by 2 equal to 0. Then V naught equal to delta VC by 2. Because VC is nothing but a V naught, because capacitor is always voltage across the load. That's voltage across the capacitor is nothing but a voltage across the load. Then what is V naught? You write VDC by 1 minus D. Delta VC is DI naught by FC. DI naught by FC. Shall we write like this? VDC by 1 minus D equal to D by FC into I naught is written as V naught by R. We simplify this, what we get? Then VDC by 1 minus D equal to then D by FC. What is V naught? You write VDC by 1 minus D. VDC by 1 minus D. 1 minus D cancel. Then VDC cancel. Then what is critical capacitance? CC equal to critical capacitance. This is 2 na? 2 FC. 2. Then critical capacitance CC equal to, this is D by 2FR. This is a critical capacitance. D by 2FR. This is a critical inductance and this is a critical capacitance. Here, this is about what is the analysis of boost regulator in the case of which mode? Continuous mode. All these formulas are given in continuous. Concentrate. In boost regulator or step up chopper, you can write one note. In boost regulator, practically for D equal to 1, for duty cycle equal to 1, V naught equal to 0. What is the reason? Actually, as per formula, what is V naught equal to? VDC by 1 minus D. You substitute D equal to 1 means, if D equal to 1, what is V naught equal to infinity? But this is ideal case. Practically it is not possible. Why for D equal to 1, V naught equal to 0? We know that If the switch is on state, in the case of boost regulator, if the switch is on state, diode is under off state now, this is capacitor. Now this is load and this one is inductor. This is the equivalent circuit during switch is on state. This equivalent circuit, you know, during switch is on state. Now during switch is on state, now capacitor will supplying the current to the load. That means capacitor acts as a short circuit. When the capacitor acts as a short circuit, what the voltage across the load? 0. That's the reason why during the switch is on state, in boost regulator, D equal to 1. What do you mean by D equal to 1? T on equal to T. T on equal to T means permanent switch on. Permanent switch on. Permanent switch on. In a permanent switch on case, always capacitor acts as a short circuit. When the capacitor acts as a short circuit, what is the voltage across the load? 0. But what about here? Inductor storing the energy. But it is unstable operation. It is unstable operation. It is unstable operation. Can you tell why it is unstable operation? Can you tell why it is unstable operation? Yes. If you permanently switch on the switch, if you permanently switch is on state, always inductor storing the energy. It never release the energy. How much time it will store? After some time, inductor will be damaged. After some time, inductor will be damaged. That's the reason why it is a unstable operation. Okay. For D equal to 1, never operate a boost regulator for D equal to 1. If you operate a boost regulator practically for D equal to 1, then permanently switch is on, the inductor will be damaged and average voltage equal to 0. It is unstable operation because inductor continuously storing the energy, then after some time it will damage. That's the reason why it is unstable operation. For D equal to 1 in a boost regulator, average output voltage is not infinity. Practically it is a 0 because capacitor acts as a short circuit. Clear? Okay. Now this is what exactly boost regulator for continuous mode. Now we'll see what is the analysis of boost regulator in discontinuous mode. Here I want to give mainly two formulas. Analysis of boost regulator in discontinuous mode. Yes, we know that in discontinuous mode means before completing one time period, current falls to 0. Then it is nothing but a discontinuous mode of operation. If you assume that this is T, then this is beta T, then what is this dt? Then what this one? IL max. This is IL waveform. In a discontinuous mode of operation, what is delta IL, you tell me? IL max. It may be buck or it may be boost regulator. This is IL max. But the IL max formula is different for buck regulator and boost regulator. Delta IL equal to IL max. Then apply volt second balance. Then according to volt second balance, VL on into T on plus VL off into T off is equal to 0. What is VL on? Voltage across the inductor during on state. In the case of boost regulator, it is VDC into T on plus what is the voltage across the inductor during off state? What is the voltage across the inductor during off state? We know that VL plus V0 equal to VDC, VL equal to VDC minus V naught. VDC minus V naught. But what is off time here? Off time. This is T on. This is T off. I already told that. In this case, off time equal to off time is written as beta minus D into T. This is beta minus D into T is equal to 0. Okay. Shall you write like this? VDC into T on is written as dt is equal to minus VDC minus V naught into beta minus D into T. T cancel. Shall you write like this? VDC D by beta minus D equal to V naught minus VDC by VDC. Shall you write like this? V naught by VDC. V naught by VDC minus 1 equal. Then what is V naught by VDC? D by beta minus D plus 1. Shall you write like this? Beta by beta minus D. From this, what is V naught equal to? Beta VDC by beta minus D. If beta equal to 1, this is average output voltage in each mode, discontinuous mode. Then if you want to get the formula in continuous mode, means you substitute beta equal to 1. You can VDC by 1 minus D. Similar to that of boost regulator in continuous mode you can get. Therefore, you know this relation, always V naught in discontinuous mode is greater than V naught in continuous mode. If you want that, check by taking D value and beta value. Okay, remaining parameters you want to calculate, same procedure what I explained in continuous mode, same procedure you follow, but you take T of is not 1 minus D into T, you take beta minus D into T. Understood? Okay, this is the fraction of duty cycle at which current is 0. This is taken as a beta. Okay, before completing one time period, current is 0. That's the reason why it is a discontinuous mode. Okay, this is the analysis of boost regulator both in continuous mode and discontinuous. Okay, continuous mode and discontinuous mode. Okay, now I want to make some summary. What is the summary of this boost regulator? Okay, then you go for what is practical analysis of boost regulator. That is a special case in the boost regulator. Practically, how to analyze this boost regulator circuit, that you will. Okay, this is clear concept. Okay, in the next class, in the next session, we will continue with for the practical analysis. After that, I will give the summary. This is better. Okay, in the summary, I will include both ideal analysis and practical analysis. Okay, we start in the next.